Hello there, and welcome to the Science for Sleep channel, a quiet place where curiosity softens into calm and the vastness of the universe becomes a gentle backdrop for rest. Tonight, we will drift together into the unknown, exploring the questions that remain unanswered in science, the enigmas that linger in the dark spaces between what we believe we understand and what still escapes us. Despite all of humanity's discoveries, despite centuries of exploration, research, and theory, the universe continues to overflow with puzzles, paradoxes, and hidden mysteries that no one can fully explain. Some of these riddles belong to the grandest scales imaginable, stretching across galaxies, drifting among clusters of stars, and spiraling around the edges of black holes, while others are woven into the fabric of our own world, tucked within the oceans, the thin layers of the atmosphere, the geology beneath our feet, and even the biology that sustains our bodies. These lingering questions remind us that science is not a completed book of absolute truths, but an ever-evolving narrative, an endless tapestry still being written with every experiment, every observation, and every new spark of curiosity. Each mystery is a doorway into wonder, a quiet reminder that we are explorers living inside a universe far larger and more intricate than we can currently comprehend. If drifting through these scientific wonders helps you relax, feel free to like, subscribe, or share your thoughts in the comments. It helps others find their way here. But for now, let these questions carry you gently as we begin our journey. One of the oldest and deepest mysteries is the simple yet overwhelming question of why the universe exists at all. Why is there something instead of nothing? It seems like the most fundamental question imaginable, yet science has no definitive answer. Physics allows us to describe how the universe behaves once it is already here. Cosmology can trace its origins back to the Big Bang, mapping the history of cosmic evolution. But what brought the universe into existence in the first place, why the laws of physics exist at all, remains unknown. Quantum theory suggests that what we call nothing is not empty. Even the vacuum of space flickers with activity, filled with virtual particles appearing and disappearing in tiny bursts. Some scientists propose that the universe itself may have emerged from such a fluctuation, as though absolute nothingness is inherently unstable and must eventually give rise to something. Others argue that our universe may be only one among countless universes in an immense multiverse, each springing into existence with its own unique laws and properties. Yet this idea only pushes the question further. Why should the multiverse itself exist? Some philosophers suggest that existence might be the natural state of reality, that non-existence is impossible, that something in some form must always be. But these ideas remain beyond testing. No telescope can detect why existence exists, and no particle collider can measure the origin of being itself. Every star in the sky, every law of nature, every atom in your body rests on a foundation we cannot explain, making the simple fact that reality is here at all one of the deepest mysteries we face. Just as profound is the question of what triggered the universe to begin. We can trace cosmic history back nearly 14 billion years to a moment when everything was compressed into a blazing, dense fireball. We call this the Big Bang, but the true cause of that event remains hidden. Cosmologists have reconstructed the universe's early timeline with remarkable detail, following it from mere fractions of a second old, when an event called inflation may have caused space to expand faster than the speed of light, stretching tiny fluctuations into the seeds of galaxies. But what triggered inflation? Why did it start? Why did it eventually stop? These questions float unanswered in the darkness. Some theories imagine the Big Bang as a quantum tremor in the fabric of reality, a sudden transformation that created space and time themselves. Others imagine a universe that expands, collapses, and is reborn endlessly in a cycle of cosmic death and renewal. Yet the question becomes even more puzzling when we consider time itself. If the universe marks the birth of time, then asking what came before might not even make sense, because before may not exist in any meaningful way. Our most advanced instruments, the Hubble Space Telescope, the Planck satellite, and the powerful James Webb, can capture light from the universe's earliest eras, but none can look into the very first instant. We know the universe began. We can measure its age, chart its expansion, and observe the afterglow of its earliest light. But the true first cause remains concealed behind a veil we have not yet pierced. Another mystery woven into everyday life is the way time itself behaves. Time feels as though it flows forward, relentlessly carrying each moment into the past. We remember yesterday but never tomorrow. A broken object does not reassemble itself. Heat spreads but never recoils. This one-way movement is called the arrow of time, yet what makes it strange is that the fundamental laws of physics do not require time to move forward. At the smallest scales, particles can move forward or backward in time with equal mathematical consistency. The equations are symmetrical. Nothing in them demands that time should have a direction. Yet the world we live in depends entirely on this one-way flow. Many scientists connect the arrow of time to entropy, the natural tendency for disorder to increase. The universe began in an incredibly ordered, low-entropy state and has been drifting toward disorder ever since. But why did it begin in such a special state? Why was the cosmos born with the conditions necessary for time to move forward at all? Some think the arrow of time might emerge from the spreading of information. Others believe it is tied to the expansion of the universe itself, but none of these explanations are complete. Time's direction is something we experience constantly, yet its origin remains one of the most haunting mysteries in science. As we move deeper into the unknown, we encounter another astonishing truth. Most of the universe is made of something we cannot see. When astronomers study the way galaxies spin, they discover that stars near the outer edges move too quickly to be held by visible matter alone. By all logic, those stars should drift into space, yet they stay bound as though held by an invisible force. This has led scientists to conclude that most of the universe's mass is invisible, undetectable by traditional means. We call this mysterious substance dark matter. It neither emits nor absorbs light and cannot be seen directly. Yet its gravity shapes galaxies, bends starlight across billions of light years, and forms the scaffolding of the cosmic web. Some scientists think dark matter might be made of undiscovered particles such as WIMPs or axions, while others propose more exotic possibilities like primordial black holes formed in the earliest moments after the Big Bang. Despite decades of searching, we have not detected a single particle of dark matter. Detectors buried deep underground wait for the faintest collision between dark matter and ordinary atoms, but none have been observed. For now, this invisible mass, 5 times more abundant than the matter we can see, remains one of the universe's greatest unsolved mysteries. And still, there is yet another unknown force shaping the fate of everything. In the 1990s, astronomers studying distant supernovae expected to find that the universe's expansion was slowing down due to gravity. Instead, they found the opposite. The universe is expanding faster and faster, as though driven apart by an invisible pressure woven into space itself. This mysterious phenomenon is known as dark energy, a placeholder term for something we cannot explain. Dark energy makes up nearly 70% of the entire universe, yet we have no idea what it truly is. One possibility is that it is a property of empty space, a constant energy permeating the vacuum. Another hypothesis suggests that dark energy is a dynamic field that changes over time. Some theories even propose that this accelerating expansion means our understanding of gravity is incomplete. What makes dark energy even more unsettling is its influence on our future. If it remains constant, galaxies will drift farther and farther apart until only silence and empty space remain. If it grows stronger, it could eventually tear apart galaxies, stars, planets, and even the atoms that make up matter. We can measure its effects with remarkable precision, but its true nature remains hidden, an unseen hand guiding the ultimate destiny of the cosmos. The laws of physics appear to be calibrated with an almost impossible precision, tuned for life in a way that remains deeply mysterious and far beyond our current understanding. The universe seems balanced on a razor's edge, as though countless cosmic parameters were delicately adjusted long before stars, planets, or observers existed. If gravity were only slightly stronger, stars would collapse rapidly under their own weight. If it were a little weaker, the clouds of matter that form galaxies might never condense at all. If the electromagnetic force differed by an almost imperceptible fraction, atoms would fail to bind together, chemistry would fall apart, and the building blocks of life would not exist. Even the tiniest shift in the constants of nature could erase every possibility of biology, consciousness, or structure. This profound puzzle is known as the fine-tuning problem, and it confronts us with one of science's most unsettling questions. Why do the laws of nature possess exactly the values they have? There is no obvious reason for gravity, electromagnetism, or the nuclear forces to hold the strengths they do. And yet, if any one of them deviated by even a minuscule amount, our universe would be a barren, lifeless expanse of darkness. Some scientists argue that this extraordinary alignment is nothing more than coincidence. Others propose the idea of a vast multiverse in which countless universes, each with different physical laws and constants, exist side by side, and we simply inhabit the rare one where conditions permit life, a cosmic lottery win so improbable that it defies imagination. Another possibility is that there is some deeper, still undiscovered principle or law that forces the constants of nature to adopt these exact values, a hidden mechanism that sets the stage for a universe capable of complexity. For now, we don't know, but every time we look at the stars, the planets, and the very fact that we are able to question our own existence, we are reminded that the universe feels improbably and almost uncannily suited for life, and why that is remains one of the greatest scientific mysteries. Equally puzzling is the question of the universe's true size. No one knows whether the cosmos extends forever or ends somewhere beyond our sight. The observable universe spans roughly 90 billion light-years across, a staggering expanse, yet we cannot see beyond this boundary because light has had only so much time to travel since the Big Bang. This creates a cosmic horizon, a limit beyond which we cannot look. What lies past that invisible edge is unknown. One possibility is an infinite universe stretching endlessly in all directions, filled with uncountable galaxies, stars, and possibly other Earth-like worlds. Another possibility is that the universe is finite but unbounded, like the curved surface of a sphere, where traveling far enough in one direction might eventually bring you back to your starting point. Scientists examine the cosmic microwave background, the faint afterglow of the Big Bang, in hopes of finding clues to the universe's shape and structure. So far, the evidence suggests that the cosmos is nearly flat, but this does not settle whether it is infinite or loops back on itself. The true form of the universe remains hidden beyond our grasp, along with whatever lies outside the observable horizon. When we observe distant galaxies, we are also looking back in time, because their light has taken billions of years to reach us. The farthest galaxies we can detect show us the universe as it was over 13 billion years ago, but beyond that lies a permanently concealed region, the unobservable universe. This boundary is not a physical wall but a limit imposed by the age of the cosmos and the finite speed of light. Reality continues beyond the horizon, but we cannot know exactly what exists there. It might simply be more galaxies and stars stretching infinitely, or it could be regions governed by different conditions or even different physical laws. Some versions of inflation theory, the idea that the early universe expanded at an enormous rate, suggest that our observable universe is merely one bubble among many in a larger, incomprehensibly vast cosmic foam. If this is true, then most of reality lies forever beyond our ability to measure, and we inhabit a small cosmic island floating in a much larger ocean of existence. Some scientists even argue that entirely separate universes could exist, giving rise to the bold and controversial multiverse idea. In this view, our universe may be only one of countless others, each with different laws, different histories, or even different numbers of dimensions. Inflation could create separate bubble universes with unique conditions, and string theory predicts an enormous landscape of possible realities. In such scenarios, our universe is simply one outcome among many, and fine-tuning might be explained by the idea that only universes capable of supporting observers can ever be noticed. But there is a problem. If other universes exist beyond our cosmic horizon, no light or signal could ever reach us, making the multiverse untestable and blurring the line between science and speculation. Still, the possibility that existence extends far beyond our universe remains one of the most captivating mysteries in modern physics. Questions about the fundamental nature of reality lead us to space and time themselves, which may not be solid and unchanging but dynamic and flexible, as shown by Einstein's general relativity. Space and time bend, stretch, and warp, guiding the motion of planets and the paths of light. But what is the deeper fabric of space-time made of? At the smallest scales, relativity and quantum mechanics clash. Relativity paints space-time as smooth and continuous, while quantum mechanics predicts fluctuations, uncertainty, and granularity. Reconciling these opposing views is one of science's greatest challenges. Some theories propose that space and time are not fundamental at all but emerge from a deeper substrate, perhaps a network of quantum information or patterns of entanglement that collectively generate geometry. In this picture, space-time is like the surface of a deeper, unknown reality. Some researchers even question whether time itself truly exists or if it is an illusion created by more fundamental processes. If so, our everyday intuition about reality would be profoundly mistaken. Space and time feel like the stage on which the universe unfolds, yet the stage may not be what it appears. At the quantum level, the mysteries only deepen. A single particle can exist in two places at once, a phenomenon known as superposition, and no one fully understands how or why. Quantum mechanics tells us that particles do not occupy definite positions until they are measured. Instead, they exist as clouds of probability, where many outcomes coexist simultaneously. An electron can pass through two slits at the same time, interfering with itself like a wave. Only when we observe the particle does it take on a definite state. This is not just theory. It has been demonstrated experimentally not only with electrons but with large molecules and even small groups of atoms. Physicists can create delicate quantum states in which objects exist in overlapping possibilities. What this means is still unclear. Does the particle literally occupy multiple places? Or does superposition represent our incomplete knowledge of a deeper reality? Some interpretations suggest that reality splits into multiple branches, each representing a different outcome. Others argue that reality is inherently fuzzy until measurement occurs. Whatever the explanation, superposition remains one of the most astonishing features of quantum theory. Even stranger is quantum entanglement, where particles become linked in such a profound way that the state of one instantly correlates with the state of another, regardless of the distance between them. Einstein famously called this spooky action at a distance because it seemed to violate the universal speed limit set by light. Yet countless experiments have confirmed that entanglement is real. Photons, electrons, and even small atomic systems have been entangled and separated by great distances, and the connection between them remains perfect, though no signal appears to pass between them. It's as if nature keeps a hidden ledger ensuring all outcomes match. What this means for reality is unclear. Some physicists suggest the universe is fundamentally non-local, woven together in ways that transcend the classical structure of space and time. Others propose the existence of hidden variables or deeper layers of reality that we have not yet discovered. We use entanglement in quantum computing and secure communication, but we still do not know why it works. The universe whispers across distance, and we do not yet understand the language. And then there is the measurement problem, the bizarre fact that observing something seems to change what it is. In the famous double-slit experiment, particles behave like waves when unobserved, creating interference patterns. But the moment we measure which slit a particle passes through, the wave behavior collapses, and the particle behaves like a tiny bullet. The outcome changes simply because we looked. One explanation is that the wave function, a mathematical description of all possibilities, collapses into a single outcome during measurement, but what causes that collapse remains one of the deepest unsolved questions in physics. The question of what truly counts as an observer remains one of the most confusing and controversial puzzles in quantum physics, because no one can say with certainty whether an observer must be a conscious mind, a measuring device, or simply any interaction that makes information about a system irreversible, and this ambiguity leaves room for radically different interpretations of reality itself. Some physicists argue that wave function collapse is not a real physical event at all, but merely an illusion created by deeper laws we have not yet discovered, while other interpretations claim that every possible outcome actually happens, branching into multiple parallel universes where each version of an event plays out in its own distinct reality. Still others suggest that particles appear definite only when information about them becomes encoded in the environment in a way that cannot be undone. None of these ideas has been proven, and the strange truth is that the boundary between observer and observed is far blurrier than scientists once believed. Somehow, the universe seems to behave differently depending on whether it is being watched, and no one knows why or what this implies about the nature of existence. A similar mystery surrounds gravity, the weakest of all the fundamental forces, and yet the one that shapes the cosmos on the grandest scales. Gravity holds planets in orbit, sculpts galaxies, governs the motions of stars, and anchors the large-scale structure of the universe. But compared to the other forces of nature, it is astonishingly feeble. A small refrigerator magnet can easily overpower the gravitational pull of the entire Earth, and yet we have no explanation for why gravity is so much weaker than electromagnetism or the strong and weak nuclear forces. This enormous difference in strength, known as the hierarchy problem, has puzzled physicists for decades. Some propose that gravity may leak into hidden extra dimensions that we cannot perceive, weakening the force we experience. Others suspect that gravity's true scale might be strong, but it is concealed by unknown physics at extremely small distances. Whatever the answer, the weakness of gravity is not a trivial curiosity. It is a fundamental requirement for stars to shine, planets to remain stable, and complex structures to form. Without gravity's softness, the universe as we know it could not exist. Yet another deep conflict lies between Einstein's general relativity and quantum mechanics, two theories that work flawlessly within their separate domains but refuse to merge into a single coherent description of nature. General relativity explains gravity and the structure of spacetime on cosmic scales with unmatched precision, while quantum mechanics accurately describes the behavior of particles and forces in the microscopic world. Both theories have survived every experimental test we can devise, yet when we try to apply them together, such as in the extreme conditions inside black holes or during the earliest instance after the Big Bang, the mathematics explodes into infinities and contradictions. Physicists have searched for decades for a theory of everything that unifies them, exploring ideas like string theory, loop quantum gravity, and other proposals that attempt to quantize spacetime itself. But despite their elegance, none of these candidates has been experimentally verified, leaving us uncertain about the true nature of reality at its deepest levels. This incompatibility represents one of the most profound paradoxes in modern science. Our two best theories cannot both be fully correct, yet each works perfectly wherever we can test it. Nowhere is this conflict more visible than in the mysterious interior of black holes, where gravity becomes so strong that the known laws of physics appear to collapse. Black holes form when massive stars die and their cores collapse under their own gravity, compressing matter into a region so dense that nothing, not even light, can escape. According to Einstein's equations, all the matter falls toward a singularity, a point of infinite density and zero volume. But infinities in physics usually signal that our theories have reached a limit rather than revealing something literal about nature. Many scientists believe the singularity is not a real physical point but a placeholder, marking where a deeper theory, perhaps quantum gravity, must take over. That theory might reveal a finite core, a loop of spacetime, or some new state of matter beyond anything we can currently observe. The event horizon of a black hole hides its interior completely, ensuring that the true heart of a black hole remains sealed beyond our reach and perhaps forever beyond observation. Singularities appear not only inside black holes but also in our equations describing the Big Bang, suggesting that the universe itself may have begun from a state where our physics breaks down. Whether singularities exist in nature or whether they merely indicate the failure of our current theories remains one of the biggest unanswered questions in cosmology. These puzzles lead directly into one of the most persistent mysteries in theoretical physics: the black hole information paradox. Information about a physical system, its particles, states, and configuration, is supposed to be preserved according to the laws of quantum mechanics. But when matter falls into a black hole, it seems to disappear forever. Unless something saves that information, the fundamental rules of quantum theory would be violated. Stephen Hawking showed that black holes should emit faint thermal radiation, now known as Hawking radiation, due to quantum effects near the event horizon. Over unimaginable lengths of time, this radiation could cause black holes to evaporate completely. But if a black hole disappears, what happens to the information that fell inside? If it is destroyed, quantum mechanics breaks. If it escapes, then somehow the information must be encoded in the Hawking radiation, despite that radiation appearing random and featureless. Some theories propose that information is stored on the event horizon itself like a hologram. Others suggest that black holes might connect to other regions of spacetime, allowing information to escape through wormholes or tunneling processes. Still, others argue that our understanding of quantum mechanics must be revised to solve the paradox. The fate of information in black holes touches the deepest foundations of reality, and after decades of debate, no consensus exists. Hawking radiation itself remains theoretical. Although it is one of the most profound predictions of modern physics, we have never directly detected it. Real black holes are surrounded by extreme environments, hot gas, radiation, and turbulence that overwhelm the faint signal predicted by Hawking's calculations. While laboratory analogs involving sound waves or fluid systems have produced hints of similar behavior, these experiments cannot fully confirm the phenomenon. If Hawking radiation is real, it has enormous implications. Black holes would have temperatures, entropy, and thermodynamic behavior, suggesting that spacetime is far more dynamic and quantum in nature than we once thought. If Hawking radiation does not exist, then something even stranger must occur at a black hole's boundary. Even more speculative is the idea that black holes might serve as gateways to other worlds or entirely new regions of spacetime. Certain solutions to Einstein's equations allow for wormholes, hypothetical tunnels linking distant areas of the universe or even separate universes. Some physicists have proposed that the singularity inside a black hole could lead to the birth of a new universe with its own independent laws of physics. Others imagine that black holes recycle information or act as cosmic seeds for future regions of space and time. These ideas remain untestable, as no signal can escape a black hole's interior, but they capture the imagination precisely because black holes sit at the edge of what physics can describe. Finally, even some of the earliest chapters of cosmic history remain hidden in mystery. We still cannot fully explain how the very first stars, known as population 3 stars, formed. In the early universe, after the Big Bang, the cosmos consisted only of hydrogen, helium, and a trace of lithium. There were no heavier elements, no dust grains, no complex chemistry, just expanding clouds of primordial gas. At some point, these clouds collapsed under gravity to ignite the first stars, ending the cosmic dark ages and illuminating the universe for the first time. These primordial stars would have been colossal, hundreds of times more massive than the sun, burning fiercely and living short, violent lives before exploding as powerful supernovae. Their formation, structure, and fate remain major open questions, partly because no population 3 star has ever been directly observed. They existed too long ago and lived too briefly, leaving behind only indirect signatures in the distribution of elements and the earliest structures we can detect. Understanding how these first stars formed is essential for explaining how the universe transitioned from darkness into a place filled with galaxies, planets, and eventually life. Yet, like so many mysteries in cosmology, the details remain just out of reach, waiting for new observations and deeper theories to reveal how the universe first lit itself from within. The earliest stars, known as population 3 stars, forged the first heavy elements and seeded the young universe with the building blocks that future generations of stars, planets, and ultimately life would depend on. Yet, despite their fundamental role in cosmic history, not a single one has ever been directly observed because they formed so early, lived so briefly, and died so violently that all direct traces have vanished, leaving astronomers to search for indirect evidence hidden within the chemical signatures of ancient surviving stars, hoping to uncover hints of those first titanic explosions as observatories like the James Webb Space Telescope attempt to peer far enough back in time to catch even a faint whisper of their light. But until such a moment arrives, the exact chain of events that ignited the universe's first stellar generation remains one of astronomy's most profound unsolved mysteries. Compounding that mystery is the discovery that some galaxies formed supermassive black holes far earlier and far more rapidly than current theories can account for, because at the center of nearly every galaxy lies one of these immense gravitational monsters, millions or even billions of times more massive than the sun. And while we understand that black holes can grow through the steady consumption of gas, stars, and even mergers with other black holes, observations of the early universe reveal behemoths that expanded to colossal size in impossibly short cosmic intervals, some already fully formed less than 1 billion years after the Big Bang, when standard growth models say there simply wasn't enough time or material available. This inconsistency forces scientists to consider radical alternatives, such as the direct collapse of enormous primordial gas clouds that bypassed normal star formation entirely, or the deaths of ultramassive first-generation stars collapsing into unusually large black hole seeds, or perhaps even an unknown process enabling growth rates far beyond anything yet identified, making these early black holes powerful challenges to our understanding of galaxy evolution and cosmic structure, standing as ancient anomalies that appear to have grown faster than the universe should have allowed. On a more visible scale, even the majestic spiral shapes of galaxies remain an unresolved puzzle, for although spiral galaxies like the Milky Way dominate astronomical imagery with their sweeping, curved arms of dust, gas, and stars unfurling like cosmic pinwheels, no single explanation fully accounts for why these elegant structures form or how they maintain stability over billions of years. One prominent theory suggests spiral arms are density waves, similar to traffic clusters on a highway, where stars temporarily bunch up as they orbit, creating the illusion of apparently permanent arms, while another theory proposes that gravitational encounters and tidal interactions between neighboring galaxies may stir stellar disks into curved, flowing patterns. Yet computer simulations, despite being incredibly advanced, still fail to replicate spiral galaxies with complete consistency, leaving their origin and persistence only partially understood. So every time we look up at the glowing band of the Milky Way stretching across the night sky, we are admiring a structure that remains both familiar and scientifically unresolved. Meanwhile, the universe continues to deliver sudden and perplexing signals in the form of fast radio bursts, brief, incredibly powerful flashes of radio energy first detected in 2007, lasting only a few milliseconds yet releasing as much energy in that instant as the sun emits over an entire year. And although hundreds of these bursts have now been observed across the sky, their origins remain obscure, with some bursts repeating in patterns that suggest ongoing activity from sources like magnetars, extremely magnetic neutron stars capable of violent outbursts, while others occur only once, hinting at catastrophic one-time events such as collapsing stars or merging compact objects. Yet no single model explains the full variety. These fast radio bursts travel across billions of light years, stretched and distorted by the matter they pass through, offering the possibility of mapping the universe's structure. But until their origins are known, they remain mysterious cosmic messages, whose senders we cannot yet identify. Related to these unexplained signals are pulsars, discovered in 1967, which are rapidly spinning neutron stars, the dense remains of massive stars, that sweep beams of radiation across space with such perfect regularity that their timing initially led scientists to wonder whether they might be artificial signals from extraterrestrial civilizations. Today, we know pulsars are natural, but their precision remains astonishing, with some pulsars rotating hundreds of times per second and keeping time, with an accuracy surpassing even our finest atomic clocks. An extraordinary stability maintained despite being objects of unimaginable density crushed into spheres only the size of a city. And although their magnetic fields and superfluid interiors are believed to stabilize their spin, the underlying physics is still not fully understood, especially when pulsars suddenly glitch, abruptly changing their rotation speed in ways we cannot yet predict, pointing to exotic processes occurring deep within their superfluid, superdense cores, regions where matter behaves unlike anything found on Earth. Even more extreme than pulsars are magnetars, neutron stars with magnetic fields 1,000 times stronger than typical neutron stars and 1,000,000,000,000 times stronger than Earth's magnetic field, capable of twisting and straining under their own magnetic tension until they violently snap, unleashing eruptions of X-rays and gamma rays so powerful that a single burst can release more energy in 1 second than the sun produces in 100,000 years. Yet the mechanisms behind these violent explosions remain uncertain, with theories ranging from seismic starquakes cracking their crust under magnetic pressure to sudden reconfigurations of magnetic field lines, releasing enormous amounts of stored energy like a cosmic rubber band snapping. And while some fast radio bursts have been linked to magnetars, suggesting they may explain at least a portion of those enigmatic signals, the complete picture remains elusive since magnetars are rare, only a few dozen known, but they represent some of the most powerful and least understood engines in the universe. The mysteries deepen as we consider cosmic rays, high-energy particles that bombard Earth every second, many originating from the sun or supernova explosions, but a rare subset possessing so much energy that no known astrophysical process should be capable of accelerating them to such extremes, with the most energetic cosmic rays carrying the kinetic energy of a fast-thrown baseball compressed into a single proton. These ultra-high energy particles may originate from active galaxies, supermassive black holes, or exotic processes entirely unknown. Yet tracing their origins remains difficult because magnetic fields throughout space bend their paths, erasing directional clues before they reach Earth, leaving observatories like the Pierre Auger Observatory in Argentina working to unravel their origins by studying the particle showers they produce when striking Earth's atmosphere. But the deepest mysteries persist, reminding us that somewhere in the cosmos, nature operates. Particle accelerators far more powerful than anything humanity can construct. Finally, zooming out to the largest scales of existence reveals vast cosmic voids, immense regions almost entirely devoid of galaxies, spanning hundreds of millions of light years and forming part of the universe's grand cosmic web in which galaxies cluster along filaments and walls surrounding these enormous empty spaces. And while simulations suggest gravity naturally pulls matter into dense structures leaving empty regions behind, the largest voids exceed predictions and raise questions about whether they are statistical anomalies or signs of deeper physics related to dark energy or the universe's expansion. These voids affect how light travels, subtly distorting cosmic measurements, and might even hold clues about the fundamental nature of the universe. Yet they remain among the most desolate and least understood regions in existence, vast abysses of near-nothingness whose origins and significance continue to puzzle astronomers and cosmologists attempting to map the structure of everything that exists. The ultimate fate of the universe remains one of the most profound and unresolved questions in modern science, a mystery that stretches across cosmology, physics, and the limits of human imagination. Although we understand with strong confidence that the universe had a beginning in the explosive expansion of the Big Bang, whether it will experience a definite ending is still unknown. Scientists examine several theoretical outcomes, each shaped by the nature of dark energy and the complex interplay of cosmic forces that govern expansion. In one widely considered scenario, the universe may continue expanding forever, gradually cooling as stars exhaust their fuel, galaxies drift apart into immense isolation, and matter itself grows cold and inert, leading to the bleak and silent state known as heat death. Another possibility is that the expansion could slow down and ultimately reverse, causing all galaxies, stars, and cosmic structures to collapse inward in a catastrophic event called the Big Crunch. A far more violent alternative is the Big Rip, a hypothetical future in which dark energy grows increasingly powerful over time, eventually overcoming gravity, tearing galaxies apart, then ripping stars, planets, molecules, and even atoms themselves into fragments as space-time disintegrates. Despite extensive observations suggesting that universal expansion is accelerating, the true nature and long-term behavior of dark energy are so poorly understood that scientists cannot yet determine which fate awaits the cosmos. The universe might endure for unimaginable trillions of years, or it could end in a dramatic collapse or disintegration long before that. Our uncertainty about the universe's ending mirrors our uncertainty about its earliest moments, particularly the mysterious event known as cosmic inflation. In the first tiny fraction of a second after the Big Bang, the universe is believed to have expanded faster than the speed of light, smoothing out space-time and stretching microscopic quantum fluctuations into patterns that later grew into galaxies and clusters. Yet what triggered this rapid expansion remains unknown. Some theories propose a unique energy field, sometimes called the inflaton, that dominated the young universe before vanishing, while others suggest inflation was rooted in the quantum structure of space-time itself. Evidence for inflation is etched into the cosmic microwave background radiation, the faint glow left behind by the Big Bang, where temperature variations match predictions, but the fundamental cause of this cosmic growth spurt, and whether inflation unfolded exactly as current models describe, is still debated. Something unleashed an unimaginably fast expansion and set the stage for everything that followed. Yet the true spark behind creation remains concealed. This pattern of deep uncertainty continues when we turn from the origins of the universe to the origins of life on Earth. Life began more than 3.5 billion years ago, but the precise steps that transformed non-living chemistry into the first biological systems are still hidden in the distant past. Fossil evidence shows that microorganisms existed relatively soon after Earth cooled, but what allowed non-living molecules to cross the threshold into life is still unclear. One hypothesis proposes that life began with simple, self-organizing molecules capable of storing information, such as RNA, which may have preceded DNA. Another popular idea is that life emerged in the mineral-rich environments of deep-sea hydrothermal vents, where hot water and chemistry created ideal conditions for complex reactions. Others argue that essential ingredients for life may have arrived from space aboard comets, meteorites, and interplanetary dust that struck the early Earth. Although scientists have successfully produced amino acids and other basic building blocks under simulated early Earth conditions, no experiment has created a fully self-sustaining living system. Life's emergence may have required a rare combination of conditions, or it may be a natural outcome whenever the right chemistry is present. Even the environment that hosted the first life remains uncertain. The deep ocean provides stability, abundant chemistry, and access to continuous energy, making hydrothermal vents strong candidates. Yet the immense water volume makes it difficult for molecules to concentrate. On the other hand, shallow pools on land, which repeatedly filled and dried, may have concentrated organic molecules and exposed them to ultraviolet light that could power important reactions, but such environments were potentially unstable. Until more conclusive evidence is discovered, we cannot say whether life first stirred in the deep sea or in sunlit pools on land. The answer is locked within ancient rocks and fossils that have long since changed beyond recognition. The formation of the first cell adds another layer of mystery. Modern cells are astonishingly complex, containing membranes, specialized structures, metabolic machinery, and precise biochemical processes. Yet the earliest protocells were likely simple, fragile systems. Fatty molecules that naturally formed on the early Earth may have assembled into small bubbles, trapping useful chemicals and creating protected environments where early metabolic reactions could take place. Inside these primitive compartments, molecules such as RNA or early proteins might have performed simple catalytic tasks. Experiments have shown that membranes can form spontaneously under the right conditions, but the transition from basic chemical bubbles to fully organized, self-sustaining cells is still not understood. Another fundamental mystery lies at the heart of life's information system: DNA. All life on Earth uses DNA's elegant double helix structure to store and transmit genetic instructions. But the reason DNA became the universal molecule of life is unknown. Chemistry permits many possible information-carrying molecules, and RNA is simpler and likely older, yet DNA eventually took over as life's primary code. Its stability, reliability during replication, and capacity for immense information storage make it an ideal system. But we do not know whether DNA's dominance was inevitable or simply the result of a fortunate evolutionary accident. The question highlights deeper mysteries about the chemistry that shaped early life. Viruses present yet another puzzle. They are not alive in the traditional sense because they cannot reproduce without infecting living cells. Yet they evolve rapidly, influence ecosystems, and alter the genetic makeup of life on Earth. Their origin is uncertain. They might be remnants of ancient RNA-based organisms, fragments of genetic material that escaped from early cells, or descendants of fully living organisms that eventually lost the machinery needed for independent life. It is possible that viruses emerged through multiple pathways. They are ancient, adaptable, and may have played an important role in helping complex life evolve by transferring genes between species. Yet their beginnings remain an enduring mystery. Beneath all these questions lies an even more fundamental puzzle. Why, among countless molecular combinations generated on early Earth, did only a very small subset manage to organize into systems capable of replication and evolution? The early Earth was rich in chemical activity, producing amino acids, nucleotides, and other complex molecules in environments ranging from deep-sea vents to volcanic lakes to atmospheres electrified by storms. Yet only a fraction of this chemistry led toward life. What special properties allowed some molecules to cross that threshold while others remained inert? Was life an inevitable result of physics and chemistry, or a rare accident that occurred only once in the universe? Experiments show that many building blocks form naturally, but a truly self-sustaining, evolving chemical system has never been recreated in the lab. The leap from simple chemistry to organized biology remains vast and mysterious, leaving the origins of life and the potential for life elsewhere in the universe as one of the greatest unanswered questions in science. The uncertainty surrounding the origins and nature of life raises profound scientific questions that remain unresolved even after decades of study. If the emergence of life is an inevitable consequence of chemistry and physics wherever the right ingredients and conditions exist, then the universe may be overflowing with living worlds scattered across billions of stars and galaxies. But if life began through a rare accident, a fragile and extraordinary event produced by a unique combination of chance and environment, then humanity may truly be alone in a cosmos vast beyond comprehension. The mystery of why certain molecules cross the threshold into self-replicating, evolving systems while countless others remain simple and inert stands as one of the most significant unanswered questions in modern science. Despite enormous advances, we still do not know whether life exists anywhere beyond Earth. Our planet remains the only confirmed home of biology, yet the observable universe contains an unimaginable number of stars, planets, and moons, making the idea of cosmic solitude seem unlikely. Over the past few decades, astronomers have discovered thousands of exoplanets, many orbiting in the so-called habitable zone where temperatures could allow liquid water to exist. Organic molecules have been detected on comets, in interstellar clouds, and on distant icy moons. Mars carries the imprint of ancient rivers and lakes. Europa and Enceladus conceal vast subsurface oceans warmed by tidal forces. Everywhere we look, the ingredients for life appear widespread. And yet, for all this promise, the silence remains unbroken. We have not detected a single unambiguous signal from an extraterrestrial civilization. We have found no living microbes in Martian soil, no fossils in ancient sediments, and no definitive chemical signatures in distant planetary atmospheres. Life may be common but incredibly difficult to detect, or it may be rare at every stage, requiring a delicate combination of circumstances we do not yet grasp. Until even the smallest alien organism is discovered, the question of whether life exists elsewhere remains open. Adding to this uncertainty is the possibility that alien biology may not resemble life on Earth at all. All known organisms rely on carbon-based molecules, water as a solvent, DNA and RNA to store information, and proteins to carry out cellular functions. But must life follow this blueprint? Some scientists suggest silicon could form the backbone of alien biochemistry, while others imagine forms of life adapted to ammonia-rich environments, methane oceans like those found on Titan, or even more exotic systems based on plasma, magnetic structures, or self-organizing patterns of information. Our definitions of life are biased by the fact that we only have one example to study. It is entirely possible that carbon and water are the only workable combination, but it is also possible that the universe harbors living systems so unfamiliar that they would challenge our very understanding of biology. If we ever encounter alien life, it may be unrecognizable, forcing us to rethink what it truly means to be alive. Even among worlds that appear promising, we still do not know how many are genuinely habitable. A planet's distance from its star is only one factor among many. True habitability requires a stable climate, protective magnetic fields, a suitable atmosphere, geological activity, and long-term environmental balance. Many exoplanets may be scorched by radiation, stripped of their atmospheres, tidally locked, or frozen beneath unbreakable shells of ice. Moons orbiting giant planets may host subsurface oceans, but our current instruments are too limited to explore them directly. The Milky Way might be filled with worlds capable of supporting life, or such planets may be exceedingly rare. At this stage, we cannot know. Each discovery of a new world adds a piece to the puzzle, yet the overall picture remains incomplete. This leads us back to one of humanity's oldest and most profound questions. Are we alone in the universe? For as long as people have looked up at the night sky, they have wondered whether other beings, perhaps similar to us or perhaps unimaginably different, exist among the stars. The scale of the universe, combined with the abundance of planets and the chemistry of life found across space, suggests that we should not be unique. Yet after all our efforts, listening for radio signals, scanning distant planets for biosignatures, sending probes to explore neighboring worlds, the silence remains total. It may be that life is common but intelligent civilizations are rare or short-lived. It may be that life is rare at every tier of complexity. Or it may even be that the cosmos is teeming with life, but separated from us by distances too vast or forms too alien to detect. Until we uncover evidence, We cannot escape the possibility that we are a solitary spark in an otherwise lifeless cosmic ocean, or a small voice in a vast choir we have not yet learned how to hear. Alongside these cosmic mysteries lies one equally deep within ourselves. Consciousness arises from the physical brain, yet the underlying mechanism remains unknown. Every sensation, memory, and moment of awareness corresponds to patterns of neural activity. But how these electrical and chemical signals produce subjective experience is still unexplained. Scientists can observe neurons firing, map brain regions involved in perception, and even temporarily shut down awareness with anesthesia, but none of this reveals why these processes generate an internal perspective, a sense of being. When you see a sunset, measurements can show activity in the visual cortex, but they cannot explain why this is accompanied by the vivid internal glow of red and gold. When you hear a piece of music that moves you deeply, brain scans can identify the circuits involved, but they cannot explain why those signals create emotion. Some theories propose that consciousness arises from information integrated across many brain regions, while others suggest specific neural patterns, quantum processes, or even that awareness is a fundamental property of the universe. But no theory fully bridges the gap between matter and mind. Consciousness is the most familiar aspect of existence, yet it slips beyond scientific explanation. Dreams add another layer to this mystery. Every night, the brain constructs worlds, vivid landscapes, shifting narratives, fragments of memory, and scenes filled with people both real and imagined. Despite being a universal human experience, the true purpose of dreams remains unclear. Some researchers believe dreams help the brain consolidate memories, rehearse behaviors, or regulate emotions. Others argue that dreams are simply the byproduct of neural activity during sleep, random signals woven into stories by the mind. Yet dreams can be powerful, capable of evoking terror, joy, revelation, or nostalgia. They can influence creativity and problem-solving, with many artists, writers, and scientists crediting dreams for sudden breakthroughs. What is known is that the sleeping brain is far from silent, especially during rapid eye movement phases, but the deeper meaning of dreams, if such meaning exists, remains elusive. Even the passage of time itself behaves strangely within human perception. Although clocks measure time in steady increments, our subjective experience of time stretches or compresses depending on emotion, attention, novelty, and context. Moments of fear or crisis can feel elongated, while joyful experiences or busy days seem to slip away in an instant. Childhood summers seem endless, yet adult years appear to accelerate. Some theories suggest the brain has internal timing mechanisms influenced by emotional states, while others propose that time is judged by the number of events and sensory inputs processed. The more information the brain must handle, the longer the moment feels. The more routine the experience, the shorter it seems. Yet none of these hypotheses fully explain why time in the mind behaves so differently from time on the clock. Memory, too, is filled with mysteries. Everything a person has experienced is somehow stored in the brain, yet memories are not static files. They are distributed patterns across many neural networks. The hippocampus plays a central role in forming and retrieving memories, but the precise mechanisms remain unclear. Memories can shift over time, being altered each time they are recalled. False memories can be created with surprising ease, and emotional experiences leave especially powerful imprints. Why some memories last a lifetime while others fade rapidly is not fully understood, nor is the reason certain smells or sounds can suddenly unlock vivid scenes from the distant past. Although scientists can observe individual neurons responding to specific stimuli and track brain activity patterns, the complete blueprint of memory formation and recall remains unknown. Our emotions are similarly complex and deeply rooted in both brain and body, yet their origins and mechanisms are not fully explained. Emotions shape human behavior, decision-making, and identity, but the interplay between physiology, brain regions such as the amygdala and prefrontal cortex, hormones, and sensory perception forms an intricate web that science is still unraveling. Despite remarkable advances in biology, neuroscience, and astronomy, many of the most basic questions about life, mind, and the universe remain unsolved, reminding us how much mystery still surrounds our existence. Your heart pounds when fear strikes, your stomach tightens when anxiety rises, and tears form when sadness takes hold. Yet the underlying origins of these powerful sensations remain debated and only partially understood. Scientists continue to wrestle with the question of whether emotions are ancient, hardwired survival mechanisms encoded deep within our biology, or whether they are constructed experiences shaped by culture, memory, personal interpretation, and the unique ways each brain processes the world. We know that specific brain regions play influential roles. The amygdala responds to threats, the insula reacts to disgust, and the prefrontal cortex helps regulate, interpret, and restrain our impulses. But there is no single emotional command center, no master switch we can point to. Music can send chills racing down the spine. A familiar scent can unlock long-buried nostalgia. And sometimes emotions arise for reasons we cannot name, guiding our decisions even when logic protests. Their intensity and unpredictability make emotions one of the most intimate mysteries of human existence. Creativity adds yet another layer of wonder, appearing in sudden flashes that feel spontaneous and almost magical. An artist may stare at a blank canvas for hours, a writer may struggle with an empty page, and a scientist may wrestle with a stubborn problem until, without warning, a solution arrives with clarity and force as if from nowhere. Some researchers describe creativity as the brain rearranging old ideas in new combinations, while others argue that stepping away from a problem allows the subconscious mind to work in the background. Many historical breakthroughs emerged not at desks but during walks, dreams, baths, or idle moments when the conscious mind was quiet. Brain imaging studies reveal that networks responsible for generating ideas and networks that evaluate them operate in tandem. But these findings still do not explain that moment of insight, the sudden appearance of something new where nothing existed a moment before. Why some people produce endless ideas while others struggle remains another mystery. Déjà vu, one of the strangest quirks of human perception, deepens the enigma of the mind. You may step into a place you have never visited and feel with eerie certainty that you have already lived that moment, as if time has doubled and the present is a repeat of something forgotten. Scientists have proposed many explanations: that the brain misfires and triggers a false signal of familiarity, that one part of the brain processes information slightly before another, or that a forgotten memory shares similarities with the current scene and tricks the mind into believing it is reliving something. What makes déjà vu so mysterious is the intensity with which it strikes, often lasting only seconds but leaving a long-lasting impression of duplication, reminding us how fragile and imperfect memory and perception truly are. The placebo effect adds yet another layer of complexity to the relationship between mind and body. Imagine taking a pill you believe will ease your pain, and then feeling genuine relief even though the pill contained no active ingredient. The placebo effect is not a trick or illusion. It is a measurable, physical response. Placebos have been shown to reduce pain, lift mood, calm symptoms of neurological conditions, and trigger biochemical changes in the brain, including the release of natural painkillers and changes in neurotransmitter activity. What is even more remarkable is that placebos can sometimes work even when patients are told they are taking one, suggesting that belief, expectation, and the rituals surrounding treatment activate hidden healing pathways. Yet why some individuals respond strongly to placebos while others remain unaffected is still unknown, underscoring how intricately the mind and body are linked. Even sleep, one of the most universal human behaviors, remains mysterious. Every night we surrender consciousness for hours, rendering ourselves vulnerable despite the risks this posed throughout evolutionary history. The fact that every species sleeps in some form suggests that sleep is fundamentally important, but scientists still cannot agree on its single essential purpose. Some theories suggest sleep allows the brain to consolidate memories and strengthen learning. Others propose that sleep clears out metabolic waste, restores energy, balances neural connections, regulates emotions, and fortifies the immune system. Yet none of these explanations alone accounts for all the observations. Different animals display remarkably different sleep patterns. Dolphins sleep with half their brain awake, birds can sleep while flying, and certain creatures hardly sleep at all. But one thing is clear: without sleep, the mind and body quickly deteriorate. Why we spend roughly a third of our lives in this vulnerable state remains one of biology's great puzzles. Aging, too, is a process we all experience but do not fully understand. With time, skin wrinkles, hair grays, muscles weaken, and organs begin to falter, but the fundamental reasons behind aging remain disputed. Some scientists focus on DNA and telomeres, the protective caps on chromosomes that shorten each time a cell divides until the cell can no longer replicate. Others point to cumulative damage, where reactive molecules and environmental stress slowly corrode cells. Evolutionary theories propose that aging is a trade-off. Energy devoted to reproduction early in life leaves less available for long-term maintenance. Yet nature does not follow a single rule. Some species, such as certain turtles, fish, and even jellyfish, show extremely slow aging or can reverse their life cycle entirely. Naked mole rats defy many expected signs of age, suggesting that the biology of aging is far more complex than our species demonstrates. Why humans age predictably while other organisms resist decline remains unresolved. Understanding these differences could transform medicine, but for now the mechanism of aging remains partly hidden. The upper limit of human lifespan is equally uncertain. The longest documented human life ended at 122 years, but scientists still debate whether this represents a hard biological ceiling or simply an extraordinary exception. Some researchers argue that human biology imposes a strict limit due to the body's diminishing ability to repair itself, especially past age 110 where survival rates drop sharply. Others believe there is no fixed maximum and that aging merely increases the likelihood of frailty, disease, and chance events. Although average life expectancy has climbed dramatically over the past century, the maximum age individuals reach has barely changed, rarely extending beyond 115 regardless of culture or era. Researchers investigate families of exceptionally long-lived individuals, search for protective genes, and test compounds that slow aging in animals. Whether humans could someday live to 150 or beyond remains an open question. The true boundary of human longevity, if one exists, has yet to be discovered. Regeneration offers another unresolved mystery. In nature, many animals possess extraordinary abilities. If a salamander loses a leg, it grows a new one. A starfish can rebuild an arm. Certain worms can regenerate an entire body from a small fragment. Regeneration is surprisingly common throughout the animal kingdom, yet humans can regrow only the simplest structures, such as a child's fingertip under the right conditions. Why some species effortlessly perform feats of regeneration while humans cannot is still unknown. Scientists study salamanders, zebrafish, and planarian worms in hopes of uncovering the molecular instructions that control regeneration. But the underlying blueprint remains deeply complex. Unlocking this power could revolutionize medicine, offering hope for repairing organs, limbs, and tissues, but the mechanisms remain elusive. Across emotions, creativity, memory, aging, longevity, regeneration, and the placebo effect, we find a repeating pattern. The human body and mind are filled with systems that function reliably and powerfully, yet their deepest workings evade complete understanding. We navigate life guided by processes that science is still struggling to map, leaving us surrounded by mysteries woven into our biology, our perception, and our very experience of being alive. When we look at the creatures around us, one of the most haunting questions science continues to ask is why some species possess extraordinary biological abilities while humans, despite sharing much of the same genetic foundation, do not. Take salamanders, for example. When they are wounded, the cells near the site of injury undergo a remarkable reset, slipping back into a flexible, embryonic-like state capable of becoming anything the body requires. From this cellular blank slate, new tissues form with perfect organization. Muscle fibers knit themselves back together, bones rebuild their structure, and nerves reconnect as though following an ancient blueprint. Humans carry many of the same genes involved in these processes, yet for reasons still unknown, our bodies refuse to activate them in the same way. Should we ever unlock this dormant potential, the possibilities would reshape the entire landscape of medicine. Damaged hearts could regenerate their own tissue after a heart attack. Spinal cords could regrow severed connections. Lost limbs could return with full function. But despite decades of intense research, the full genetic and biochemical map of regeneration remains elusive. Nature seems to have scattered this gift unevenly, granting it to salamanders, starfish, planarians, and a handful of other species, leaving the rest of us to observe their abilities with awe. Just as regeneration raises questions, so does longevity. for certain creatures live far beyond what biological theory would predict. The general rule across the animal kingdom is simple. Small bodies live fast and die young, while large bodies move slowly and live longer. Mice survive only a few years, while elephants can live for many decades. Humans, with our unexpectedly long lifespan compared to other primates, stand out as unusual. Yet scattered across the natural world are beings that break these rules entirely. Deep beneath Arctic ice, the Greenland shark drifts through cold, dark waters for centuries, its lifespan surpassing 400 years. Bowhead whales sing haunting songs in frozen seas for more than 200 years. Naked mole rats, tiny and unassuming, live 10 times longer than mammals of similar size while showing a baffling resistance to age-related decline. Certain clams have been found alive after more than 5 centuries. Scientists have uncovered fragments of explanations. Unusually stable proteins that resist damage, DNA repair systems that function with surprising efficiency, and metabolisms so slow they seem to stretch time itself. Yet no single answer unites all these species. Each appears to have discovered its own path to a long life, its own biological key that humans do not yet know how to copy. They remind us that aging is not a universal rule, but a puzzle with many possible solutions. If we could decipher their secrets, we might one day extend human life in ways currently unimaginable. Meanwhile, some animals survive conditions that should be lethal, such as being frozen solid. Imagine your body encased in ice, your blood crystallized, your heart silent, and your tissues rigid, circumstances that would kill nearly any creature. Yet the wood frog of North America endures exactly this every winter. Its heart stops beating, its body becomes stiff, and up to 2/3 of its water content freezes. But when spring warmth returns, the frog thaws and hops away as if nothing happened. Certain insects and fish have similar abilities, and tardigrades, the nearly indestructible microcreatures known as water bears, can survive extremes far beyond freezing, including radiation, desiccation, and even the vacuum of space. How they achieve such feats remains partly hidden. Some species fill their bodies with antifreeze compounds that prevent ice crystals from shredding their cells. Others use sugars like trehalose to stabilize tissues during freezing. However, the deeper mystery remains unsolved. How their delicate organs, especially the brain, survive months without activity. If we ever master these mechanisms, we could revolutionize medicine, preserve organs far longer for transplant, develop new emergency care strategies, or even place astronauts into hibernation for extended space travel. For now, though, the secret belongs only to these resilient survivors, organisms that seem to defy the boundaries of life and death. Similarly, whales reveal another biological wonder: centuries of life with remarkably low cancer rates. The bowhead whale, capable of living for more than 200 years, glides through the icy Arctic as a symbol of endurance. What astonishes researchers is not only its longevity but its health. Despite having billions of cells and centuries of time for mutations to accumulate, cancer is surprisingly rare. This contradiction is known as Peto's paradox. Larger animals with more cells should experience higher cancer rates, yet whales, elephants, and other giants defy this expectation. In elephants, scientists have discovered extra copies of tumor suppressor genes, functioning like additional lines of defense. In whales, the answer is less clear. Perhaps they possess extraordinarily robust DNA repair systems, or perhaps their metabolism slows cellular damage. They may even harbor unique biological pathways that humans have yet to identify. Unlocking these mechanisms could transform cancer treatment, offering new strategies to prevent or halt the disease. But for now, these secrets remain hidden beneath the ocean's depths. In another realm of mystery, birds demonstrate an uncanny ability to sense Earth's magnetic field, a talent still not fully understood. Every year, migratory birds embark on journeys that span continents. Tiny warblers fly from Europe to Africa, while Arctic terns circumnavigate the globe. They travel thousands of miles with astonishing precision, even when clouds erase all visual cues. Some research suggests tiny crystals of magnetite embedded within their tissues may act as internal compasses. Other evidence points to proteins in their eyes that might allow them to perceive magnetic fields as faint patterns of light. Yet no single explanation fully accounts for their accuracy, especially when placed in unfamiliar environments. Their navigation seems to rely on a sense humans simply do not possess, an invisible layer of reality that silently guides them. Monarch butterflies, delicate and fragile, undertake one of the most extraordinary migrations on Earth. Every autumn, they travel thousands of miles from the northern United States and Canada to the same forested mountains in central Mexico. There they gather by the millions, covering trees in shimmering waves of orange and black. What makes this journey miraculous is that no individual butterfly completes the round trip. Those that return north in spring are several generations removed from the ones that began the migration months earlier, yet they arrive at the exact same groves. Scientists have identified some clues. Monarchs use the sun as a compass and adjust for the time of day. They may also sense Earth's magnetic field. But how they pass these navigational instructions across generations remains unknown. A butterfly that has never made the journey somehow knows exactly where to go, guided by a map we cannot see. Across the animal kingdom, great migrations unfold with similar mystery. Salmon hatch in mountain streams, travel to the ocean, and years later return to the very place where their lives began. Sea turtles cross entire oceans only to return to the same patch of sand where they first emerged as hatchlings. Birds, whales, and insects navigate thousands of miles with extraordinary reliability. Scientists have discovered that some species use the stars or the angle of the sun, while others may detect magnetic fields or subtle environmental cues. Yet none of these explanations fully captures the precision of their journeys. How does a bird return to the same tree each year? How does a turtle locate one specific beach after wandering an entire ocean? These ancient rhythms remain partly unexplained, written into instincts we do not yet understand. Homing pigeons add another layer to the puzzle. For centuries, humans have marveled at their ability to be released hundreds of miles from home, circle the sky for a moment, and then fly straight back to their loft with astonishing consistency. Researchers have proposed various theories. Pigeons may use the sun as a compass, sense Earth's magnetic field, or rely on an intricate map of regional sense. But none of these explanations fully capture their accuracy, especially when conditions are unfavorable. Even when skies are overcast or they are released in unfamiliar terrain, pigeons still find their way home. Their biological compass, whatever form it takes, remains a secret hidden deep within their senses. As for humans, one of our greatest mysteries is how language began. Among all the traits that define us, language stands apart as one of the most profound and uniquely human abilities. Yet its origins remain shrouded in uncertainty. Language is the tool through which we share ideas, pass down stories, build communities, and ultimately create civilizations. Yet the origins of this extraordinary human ability remain one of the greatest unresolved mysteries of our ancient past. Our closest primate relatives, chimpanzees and bonobos, express themselves through gestures, facial cues, and vocal sounds. But none of their communication systems come close to the layered complexity and limitless flexibility of human speech. At some unknown point in our evolution, our ancestors made an extraordinary leap from simple calls and signals to structured language complete with grammar, abstraction, symbolism, and the capacity to express thoughts about things not present, things imagined, and things yet to come. Researchers have proposed many theories about how this transition might have occurred. Some suggest early humans first communicated through hand signals and gestures, with spoken words developing later. Others argue that language began with rhythmic vocalizations, chants, songs, patterned calls, that gradually evolved into spoken words. Archaeological discoveries reveal that tens of thousands of years ago our ancestors were carving symbols, painting on cave walls, and creating art that suggests their minds were capable of sophisticated communication. But because sound leaves no trace in the fossil record, the first true moments of spoken language are forever lost to time. Language allows us to plan, dream, imagine, and cooperate on scales unmatched in the animal kingdom. It is both a tool for survival and a window into human consciousness. Yet the moment when our ancestors first spoke remains hidden, and we can only imagine the earliest conversations that shaped our shared history. Laughter, another universal human trait, also carries mystery. No matter where you travel in the world, people laugh. The sound transcends culture, age, and language. Even infants laugh long before they learn to speak, and groups often laugh together in ways that spread joy almost contagiously. Yet the evolutionary origins of laughter remain unclear. Some scientists suggest laughter began as a signal of safety, an instinctive way to show others that danger had passed, transforming fear into relief. Others trace its origins to early primates, whose panting noises during playful wrestling and chasing resemble the rhythm and breathiness of human laughter. But laughter is far more complex than a simple survival mechanism. It lowers stress levels, strengthens social bonds, and triggers the release of chemicals that calm the body and connect people. Curiously, we laugh not only at humor but also at awkwardness, nervousness, relief, and even sorrow. Sometimes laughter erupts at moments when it seems entirely inappropriate, leaving us with no clear biological explanation for why such a simple sound carries so much emotional weight. Laughter remains ancient, universal, and enigmatic, a form of emotional expression shared across humanity, its deepest roots still hidden somewhere in our evolutionary past. Music presents an equally profound mystery. A melody can move us to tears, a rhythm can speed our heartbeat, and a song can unlock memories we believed long forgotten. Music has no obvious survival function, yet it is woven into every known culture across human history. Scientists have proposed several theories. Perhaps music evolved as a social glue, binding early communities through dance and collective song. Or perhaps it began as a form of courtship, allowing individuals to showcase vitality, creativity, or emotional expression. Or maybe music is a byproduct of language and memory, a beautiful evolutionary accident. What makes music even more extraordinary is its impact on the human brain. Stroke patients who struggle to speak can still sing with clarity. People suffering from dementia often remember lyrics long after other memories fade. Music can synchronize the heartbeats of people in groups, soothe newborns, and rally armies. How can organized sound reach so deeply into the mechanisms of the human mind and body? Neuroscience still has no clear answer. Music remains one of the most universal yet mysterious forces in human life, an invisible thread that ties individuals and cultures together across time. Love, too, stands among the great mysteries of human existence, powerful, transformative, and deeply complex. It shapes our lives more than almost any other experience, binding parents to children, partners to one another, and friends across years, sometimes across a lifetime. Love inspires art, sacrifice, devotion, and acts of courage. While biology can reveal some elements, such as dopamine and oxytocin, chemicals linked to reward and bonding, and evolutionary theory suggests love may have developed to keep parents together long enough to raise vulnerable offspring, these explanations capture only fragments of the phenomenon. They do not explain why love can appear suddenly, overwhelming us without warning, why it lasts decades for some people and fades for others, or why humans sometimes risk everything for it even when reason advises otherwise. Love is not simply chemistry or instinct. It is shaped by memory, imagination, and story, woven from experiences unique to each person. We can track the neural activity associated with love, but not its meaning. Its full nature remains one of the most profound mysteries of the human experience. Tears add yet another layer to our emotional enigma. While tears protect our eyes by washing away debris, only humans shed emotional tears. Tears triggered by sadness, joy, frustration, relief, or even overwhelming laughter. One theory suggests emotional tears evolved as a social signal, expressing vulnerability and encouraging empathy from others. Another idea proposes that tears help release stress-related chemicals, though scientific evidence is mixed. Tears may help strengthen emotional bonds by making invisible feelings visible. But their mystery deepens when we consider that tears arise from opposite emotional extremes: grief and joy, sorrow and relief, despair and laughter. They fall silently in moments of solitude or burst forth in communal moments of connection. No single explanation accounts for all these contexts. Emotional tears remain a uniquely human puzzle, a biological response whose evolutionary origins are still unknown. Myths add another layer of mystery. A appearing across cultures in strikingly similar forms despite vast distances and little contact between ancient peoples. From deserts to islands, forests to mountains, civilizations tell stories that echo one another. Myths of great floods, powerful sky gods, trickster spirits, underworld realms, creation stories, and heroic journeys appear again and again. Why does humanity share such narrative patterns? Some scholars suggest the human mind is naturally wired for story, and that certain themes arise from universal experiences such as fear, wonder, death, and renewal. Others believe that myths spread through migration, trade, or ancient shared ancestry, leaving echoes around the world. Still others propose that myths stem from deeper patterns in the human brain, symbolic archetypes that emerge from the same psychological landscape regardless of geography. Whatever the cause, myths serve as vessels for cultural wisdom, moral lessons, and explanations for the unknown. They bind communities, preserve memory, and express collective dreams. Yet the recurrence of similar stories in places separated by oceans and mountains remains an unsolved riddle. Humanity's tendency to cooperate with strangers reveals another fascinating mystery. Compared to most animals, humans are extraordinary in our willingness to help individuals who are not family, not allies, and sometimes not even familiar. We donate blood, build communities, volunteer, and perform acts of kindness for people we may never meet. Evolutionary theory offers possible explanations. Perhaps cooperation helped early groups survive challenges, or perhaps humans evolved reciprocal altruism, helping others with the expectation that help might be returned in the future. But humans frequently go far beyond reciprocal benefit. We sometimes sacrifice resources, time, and safety with no expectation of reward. Studies show even young children demonstrate a natural inclination to help others long before they fully understand social rules. Something in our psychology appears drawn toward cooperation. Whether this instinct arose from survival, morality, or some deeper cognitive mechanism remains an open question. It is one of the most remarkable and least understood features of our species. Civilizations, too, follow mysterious patterns. Throughout history, great societies have risen, flourished, and eventually collapsed: the Maya, the Indus Valley, Mesopotamia, ancient Egypt, Rome, the Khmer Empire. Each achieved extraordinary heights of culture, science, architecture, and governance before declining or disappearing. The reasons remain heavily debated: climate change, droughts, shifting rivers, earthquakes, invasions, political corruption, resource exhaustion, or complex interactions of multiple factors. Some historians believe civilizations follow cycles of growth and collapse driven by internal dynamics, regardless of era or location. What is striking is how sudden collapse can be. Cities once vibrant with life become abandoned. Knowledge that took centuries to build can vanish in a generation. Civilization, despite its power and scale, is fragile, and the forces that sustain or destroy it are still not fully understood. Finally, we return to one of the deepest questions of all: why humans are curious. Why do we wonder? Why do we look at the stars, at the world around us, and at mysteries within ourselves, asking questions no other creature seems compelled to ask? Curiosity drives exploration, invention, science, storytelling, and discovery. It has taken us to the depths of the ocean, across continents, into the fabric of atoms, and to the edge of space. Yet its origins remain unclear. Curiosity is one of humanity's most defining traits, but we still do not know why the spark of wonder ignited in us and not in other species. Curiosity has been described in many ways, with some believing it began as a simple extension of survival, an ancient instinct that helped early humans search for food, discover shelter, detect danger, and adapt to an unpredictable world, while others argue that curiosity evolved into something far more powerful, an inner engine that pushed our ancestors to explore new landscapes, invent tools, imagine possibilities, and question realities that had never been questioned before. Yet curiosity often stretches far beyond the boundaries of survival, inspiring us to study galaxies billions of light years away, to decode languages carved into broken stones, to unravel clues left by civilizations long vanished, and to ask questions that provide no immediate benefit beyond the satisfaction of knowing. Even from the earliest moments of life, children reach toward the unknown with tiny hands, asking endless questions, testing every boundary as though curiosity were woven directly into human nature. Still, the deeper reason for this hunger for understanding, this restless inner drive to make sense of everything around us, remains unanswered. Curiosity propels science forward, shapes art, fuels discovery, and pushes humanity into realms once thought unreachable. Yet the true source of this spark, the origin of the question why, is still one of existence's enduring mysteries. Storytelling adds another layer to this puzzle. For every culture across the world, from ancient tribes gathered around crackling fires to modern societies sharing tales through screens and books, forms narratives that bind people together. Humans shape words into stories filled with heroes and villains, losses and victories, fears and hopes. Each tale crafted to entertain, to teach lessons, to preserve memories, and to inspire imagination. Some researchers believe storytelling developed to pass knowledge through generations, embedding wisdom in memorable narratives, while others think stories strengthen communities by giving people shared myths, shared values, and shared identities. Another idea suggests stories act as mental simulations, allowing us to practice emotional responses, rehearse danger, or explore choices safely through imagination. But storytelling often goes far beyond these functions, creating entire worlds that never existed, stirring emotions for characters who are not real, and lingering in our minds long after the final words fade. No other species on Earth displays this ability in such depth, raising the profound question of why humans need stories so desperately and why we return to them again and again. All we know is that storytelling is as old as language itself, threading through every culture and linking humanity across time. Yet just as human behavior holds mysteries, nature does as well. Lightning, for instance, is familiar to most as a sudden flash in the sky, a jagged spark followed by thunder. But a far stranger phenomenon exists that has puzzled witnesses for centuries: ball lightning. Instead of a brief bolt, people describe floating spheres of glowing energy drifting silently across open fields, down hallways, through barns, or even inside homes. These orbs, often the size of a grapefruit, glow in shades of orange, white, blue, or even green, sometimes hanging in the air for several seconds before vanishing or exploding with a small pop. For a long time, ball lightning was dismissed as myth or optical illusion, a trick of frightened eyes during storms, but modern scientific recordings and credible eyewitness accounts strongly suggest it is real. Yet no one knows what it is. Some theories describe plasma suspended by electromagnetic fields. Others imagine silicon particles vaporized and glowing after a strike, while some propose chemical reactions sparked by the intense energy in storm clouds. None of these explanations accounts for every sighting, especially the baffling reports of ball lightning floating through windows or solid walls without breaking them, behaving as though it ignores the laws of physics. Despite countless observations across different cultures and centuries, ball lightning remains elusive, unpredictable, and unexplained, drifting through history as one of nature's most haunting forms of ghostly fire. Another mystery of the sky emerges during powerful earthquakes when glowing lights appear above cities or flicker along the ground. These earthquake lights vary dramatically in shape and color, sometimes appearing as blue flames near the surface, sometimes as bright flashes high above the skyline, and sometimes as hovering orbs lingering near fault lines. Reports of these lights date back centuries, yet modern footage confirms they are not fiction. What causes them remains unknown. One theory suggests that intense stress in rocks during an earthquake releases electrical charges into the air, while another proposes that tectonic movements ionize nearby gases, making them glow. However, only some earthquakes produce these mysterious lights, and their appearance is unpredictable. In rare cases, they appear minutes or hours before the earthquake begins, raising questions about whether they could serve as a natural warning system, though their rarity makes study extremely difficult. Earthquake lights remain among the most eerie natural phenomena, brief flashes of otherworldly illumination in moments of destruction, reminders that Earth holds secrets written in light, fire, and stone. Yet even deeper mysteries lie beneath the surface, including the triggers behind the most catastrophic volcanic eruptions. While many volcanoes erupt with lava flows, ash clouds, or moderate explosions, some erupt with unimaginable force, releasing energy powerful enough to alter climate, block sunlight, and devastate entire regions. Scientists understand the basics. Pressure builds as magma rises, trapped gases expand, and the volcano eventually releases energy. But what causes certain volcanoes to unleash continent-shaking destruction while others remain mild or silent is still not fully understood. Some volcanoes sleep for centuries without warning before erupting violently, while others grumble with smoke and tremors for years without exploding. Events such as Krakatoa in 1883, Tambora in 1815, and Toba roughly 74,000 years ago produced eruptions so powerful they may have altered human evolution itself. Despite advances in monitoring technologies, measuring gases, tracking tremors, scanning magma chambers, scientists still cannot accurately predict which volcano will trigger a supereruption or when. Volcanoes remain reminders that Earth is alive, ancient, and capable of releasing forces far beyond our control, holding mysteries deep within their molten cores. Another ancient puzzle lies in plate tectonics, the planetary engine that shapes continents, raises mountains, and drives earthquakes. Without plate tectonics, Earth would lack its diverse landscapes, its volcanic activity, and perhaps even its ability to support life. And yet, the question of why plate tectonics began here, and why it is still active only on Earth, remains unsolved. Mars and Venus have solid, unbroken crusts, lacking any sign of shifting plates. Billions of years ago, Earth's crust somehow fractured into enormous slabs that drift, collide, and reshape the planet. Did water act as a lubricant, softening rock and reducing friction? Did Earth's internal heat reach a perfect balance, allowing the crust to split and move? Or did colossal ancient impacts crack the surface and set the plates in motion? Despite countless computer models and geological theories, no single explanation fully answers why Earth alone developed this dynamic engine. Without it, the carbon cycle might collapse, climate might destabilize, and life as we know it might never have emerged. Plate tectonics, essential to Earth's habitability, remains one of science's most profound and persistent mysteries. Equally puzzling is the origin of Earth's water. Oceans, rivers, and lakes cover most of the surface, supporting every known form of life. Yet the source of this water is still debated. One idea suggests water arrived on icy comets and asteroids during the violent early days of the solar system, delivered from space like cosmic cargo. However, the chemical signatures of many comets do not match Earth's water. Another theory proposes that water was present from the beginning, trapped deep within Earth's mantle and gradually released through volcanic activity over billions of years. It may be that both sources contributed, yet the balance remains uncertain. What is clear is that Earth's abundant liquid water makes it exceptional in the solar system. Venus lost its water to heat, and Mars lost much of its atmosphere and moisture to the cold. Somehow, Earth managed to collect and preserve vast oceans, turning the planet into a cradle for life. Every drop of water carries the untold story of its cosmic journey, a riddle stretching back to the formation of our world. Even the moon, our closest companion, holds mysteries. For thousands of years, humans saw only one side of the moon, the near side facing Earth. When spacecraft finally photographed the far side, scientists were stunned. The moon's two faces look dramatically different. The near side is dotted with dark Maria, immense plains of solidified lava, while the far side is rugged, heavily cratered, and almost entirely lacking these smooth basalt seas. Why should two sides of the same moon be so unequal? One hypothesis suggests Earth's gravity heated the near side more intensely, thinning the crust and allowing lava to flow. Another idea proposes that an ancient collision reshaped one hemisphere. Others speculate internal differences in crust thickness or volcanic activity. Yet none of these theories explains the full picture. The moon should be symmetrical, but it isn't, leaving scientists with yet another puzzle in a universe filled with unanswered questions. The far side of the moon, with its rugged craters and ancient scars, seems to preserve secrets that resist even our most advanced attempts to understand them, as though part of our closest celestial companion remains forever out of reach. Even now, while orbiters map its terrain and robotic landers touch its silent surface. This hidden hemisphere feels like a half-stranger, keeping its true story tucked beneath layers of dust and shadow. Beneath our own feet, another mystery lies buried far deeper than any human has ever traveled: Earth's core. More than 3,000 kilometers down sits a vast sphere of molten iron and nickel swirling around a solid inner center, a churning engine that generates the magnetic field protecting us from deadly cosmic radiation and the relentless stream of charged particles pouring from the sun. Without this invisible shield, Earth's atmosphere might be stripped away just as Mars's once was, leaving our world barren and exposed. Yet, despite its vital importance, we know remarkably little about how the core truly works. We cannot drill anywhere near it, so our understanding depends on indirect clues, seismic vibrations from earthquakes, ancient magnetic signatures frozen in rocks, laboratory experiments simulating extreme pressures, and complex computer models. We know that the liquid outer core moves, that its motion powers the geodynamo, and that this process creates Earth's magnetic field, but the reasons behind the field's sudden changes, its wobbles, its periods of weakness, or its complete reversals remain uncertain. The puzzle deepens when we look to other planets. Mars once possessed a magnetic field but lost it billions of years ago. Why did Earth retain its protective heart while Mars's went silent? The core continues to operate beyond our reach, its motions unseen but felt every day, from the orientation of a compass needle to the shimmering auroras dancing near the poles. Yet the mechanisms guiding this planetary heartbeat remain one of Earth's great unsolved enigmas. Compounding the mystery, Earth's magnetic poles do not stay fixed. Every so often throughout our planet's history, the poles switch places, flipping the global field so that north becomes south and south becomes north. Ancient volcanic rocks record these reversals in layers of hardened lava, their magnetic minerals frozen in alternating patterns that stretch back millions of years. The last full reversal occurred roughly 780,000 years ago, but the reasons behind these events remain unclear. Scientists believe turbulence in the liquid outer core sometimes becomes unstable, causing the magnetic field to weaken, collapse, and then rebuild itself in the opposite direction. Yet no one knows why the core becomes unstable at certain moments and not others. Some reversals happen quickly, unfolding in a matter of centuries, while others stretch across thousands of years, and sometimes the field simply weakens without flipping at all. A weakened magnetic field would expose Earth to more cosmic radiation, raising questions about whether past reversals affected ecosystems, migration patterns, or even the evolution of early humans. We do not yet know. All we do know is that Earth's magnetic field is temporary in geologic time, a feature that will shift again, its cause hidden in the swirling motion of molten metal deep below. Earth's long history of changing climates introduces yet another profound mystery: the recurring cycle of ice ages. Over millions of years, the planet has swung between frigid glacial epochs and warmer interglacial periods in which ice sheets retreat and life flourishes in new ways. Massive glaciers have advanced and withdrawn, carving valleys, sculpting mountain ranges, reshaping continents, and steering the destinies of species. But the deeper cause behind this rhythm is still debated. Some scientists point to Milankovitch cycles, predictable changes in Earth's orbit, tilt, and wobble that alter the amount of sunlight reaching different parts of the planet. Others suggest that volcanic eruptions, ocean circulation shifts, variations in atmospheric carbon dioxide, or even subtle feedback loops between ice and climate might amplify or dampen these cycles. Perhaps all of these factors interact in ways we do not yet fully grasp. What is clear is that the waxing and waning of ice has shaped human evolution and migration. Our ancestors endured harsh glacial periods, adapted to extreme climates, and spread across continents during warmer intervals. Yet the ultimate driver behind the grand rhythm of ice and thaw remains elusive, a planetary heartbeat whose timing we have only begun to understand. Another layer of Earth's history reveals even more dramatic mysteries: mass extinctions. 5 times in the deep past, life on Earth has nearly been erased. The most famous is the asteroid impact that ended the reign of the dinosaurs 66 million years ago, but earlier catastrophes were even more devastating, such as the Permian-Triassic extinction event roughly 250 million years ago, when nearly all life on Earth vanished. Researchers propose many causes: asteroid strikes, supervolcano eruptions, abrupt climate shifts, collapsing ecosystems, or toxic changes in the oceans. In some extinction events, evidence points clearly to a single cause, as with the asteroid that struck at the end of the Cretaceous. In others, multiple disasters seem to have overlapped, creating cascading failures that life could not withstand. Equally puzzling is why some species survive while others disappear. Why did mammals endure the asteroid impact while dinosaurs perished? Why do some extinctions unfold slowly while others strike in sudden geologic moments? Mass extinctions show both the fragility and resilience of life, clearing the evolutionary stage for entirely new species to emerge. Yet the forces behind these ancient die-offs, sudden and civilization reshaping, remain only partly understood. Beyond Earth, the solar system itself holds unsolved puzzles, such as the origin and age of Saturn's rings. These shimmering arcs of ice and dust, stretching across hundreds of thousands of kilometers, yet only meters thick, have mesmerized observers for centuries. For most of scientific history, we assumed the rings were ancient, forming with Saturn over 4 billion years ago. But recent data from NASA's Cassini spacecraft showed that the rings appear surprisingly bright and clean, far too pristine for their supposed age. Over billions of years, micrometeorites should have darkened them, coating them in dust. Instead, they gleam with fresh brilliance, suggesting they may be only a few 100 million years old, practically newborn in cosmic terms. If they formed recently, how did it happen? Perhaps a moon strayed too close and was torn apart by Saturn's tidal forces. Perhaps a collision between comets or icy bodies scattered debris that spread into the rings we see today. Or perhaps some entirely unknown process created them. Whatever the truth, Saturn's rings may be temporary, gradually falling into the planet and destined to vanish within the next 100 million years. We live in the fleeting era when Saturn wears this magnificent crown, its origin still one of the most beautiful mysteries in the solar system. Uranus presents another enigma. Unlike other planets, it spins on its side, rolling through space with an axial tilt of 98 degrees. One pole faces the sun for decades at a time, bathing one hemisphere in unending daylight while the other remains locked in darkness. The most widely accepted explanation is that a massive collision early in the solar system's history knocked Uranus onto its side. But such an impact should have left behind dramatic evidence, such as a large surviving moon or a clear atmospheric scar. Alternative theories propose multiple smaller impacts or gravitational interactions during the chaotic early days of planet formation. Even Uranus's magnetic field adds to the puzzle. It is strangely tilted and offset, unlike any other planetary magnetic field in the solar system. Since only Voyager 2 has visited Uranus, much of its nature remains shrouded in uncertainty, and until a new mission arrives, the sideways spinning planet continues drifting through the cold darkness, carrying a cosmic riddle no other world shares. Venus, Earth's closest sibling in size and structure, holds another bizarre mystery. It rotates backwards. On Venus, the sun rises in the west and sets in the east, and one day lasts longer than one Venusian year. Some theories argue that a giant impact reversed its spin. Others suggest that tidal forces from the sun gradually slowed and flipped it over billions of years. Another idea proposes that the planet's dense atmosphere, combined with internal dynamics, altered its rotation through frictional coupling. Yet none of these explanations fully matches the Venus we see today, with its thick, suffocating atmosphere of carbon dioxide and sulfuric acid clouds swirling above a surface hot enough to melt lead. Whatever happened to Venus, its backward spin remains one of the most striking examples of how planets that seem similar can evolve in radically different ways. At the edge of the solar system, Neptune adds its own mystery with storms that defy expectations. Despite receiving little sunlight, Neptune's atmosphere churns with winds faster than any on Earth, reaching nearly 2,000 kilometers per hour. Enormous dark storms appear and disappear unpredictably, such as the Great Dark Spot discovered by Voyager 2 in 1989, which was the size of Earth but vanished entirely when the Hubble Space Telescope observed Neptune a few years later. New storms form, drift, stretch, and dissolve with no clear pattern. Scientists debate whether these tempests are driven by internal heat, atmospheric chemistry, or complex weather dynamics unique to Neptune's deep, frigid skies. But the underlying cause remains unknown, leaving Neptune as one of the most unpredictable and least understood worlds in our solar system. Neptune remains a remote and turbulent world, a distant blue giant visited by only a single spacecraft and still wrapped in mysteries that challenge our understanding of planetary weather. Its fierce winds and shadowy storms reveal that even in the coldest, most remote regions of the solar system, chaos refuses to fade. Meanwhile, Jupiter's Great Red Spot, perhaps the most iconic storm in our planetary neighborhood, has raged with relentless power for centuries. A colossal vortex so immense that Earth could fit inside it. For as long as humans have lifted telescopes to the sky, this swirling oval has remained etched into Jupiter's atmosphere, a storm that has persisted for at least 3.5 centuries and possibly far longer, yet still defies complete explanation. Its origins are unknown, its longevity puzzling, and its ultimate fate uncertain. This immense anticyclone, turning counterclockwise in Jupiter's southern hemisphere and powered by the planet's deep, roiling atmosphere, once spanned enough space to engulf 3 Earths. Today, it stretches across barely one, slowly shrinking in size as scientists debate whether it will someday fade entirely or transform into something new. Why this storm appeared where it did, why it has endured when storms on Earth last mere weeks, and whether it cycles through phases of strength and decay are questions still awaiting answers. In many ways, the Great Red Spot stands as a cosmic contradiction, ancient yet fragile, vast yet vulnerable, one of the sky's grandest unsolved enigmas. Far beyond it, comets gather in a distant reservoir that no instrument has ever glimpsed directly. These icy wanderers, with their glowing tails that have fascinated humans for thousands of years, sweep inward from the outermost edges of the solar system, loop around the sun, and vanish again into the black. Astronomers believe they originate from the Oort cloud, a colossal sphere of icy debris left over from the solar system's formation. This silent frontier may contain trillions of frozen bodies and stretches so far that its outer boundary could blend seamlessly into interstellar space. Yet it remains completely invisible, its inhabitants too small, too cold, and too distant to detect. All we know of it comes from the comets it occasionally sends sweeping toward our world, brief messengers hinting at the vast unseen realm that surrounds us. How the Oort cloud formed, whether it reaches farther than we imagine, and what ancient secrets it preserves are questions still unanswered, making it one of the most elusive features of our celestial neighborhood. Closer to home, many of the solar system's moons hide deep oceans beneath blankets of ice, but what lies within those lightless waters remains unknown. Water, once thought rare, turns out to be abundant far from Earth. Worlds such as Europa, Enceladus, and Titan possess global oceans beneath frozen crusts, and some of these hidden seas may contain more water than all of Earth's oceans combined. These subsurface oceans remain liquid because tidal forces from their parent planets need their interiors and generate heat. On Earth, wherever liquid water exists, life almost always follows, even in places devoid of sunlight, such as hydrothermal vents teeming with strange and resilient organisms. This raises the profound question of what kinds of ecosystems might exist beneath alien ice. Enceladus in particular has offered tantalizing hints, spraying plumes of water vapor into space that contains salts, organic compounds, and chemical traces associated with habitability. Europa's fractured surface also suggests motion and activity far below. But the oceans themselves remain hidden, their contents invisible to us, leaving open the possibility that anything from simple microbes to complex, unknown life forms could be swimming in the darkness. Until new missions penetrate these icy shells, the secrets of these subsurface seas remain locked away. Enceladus, despite being a small and unassuming moon only about 500 kilometers across, continues to astonish scientists with its dramatic geysers erupting from cracks in its southern hemisphere. These jets, discovered by NASA's Cassini spacecraft, shoot water vapor and ice grains high into space, providing a direct window into the moon's global ocean. The plumes contain organic molecules and chemical signatures that on Earth would point toward hydrothermal activity, stirring hopes that warm seafloor vents may exist beneath the icy crust. Yet the mechanism powering Enceladus's eruptions remains a mystery. Are they driven by heat from deep hydrothermal sources, or by some other process entirely unknown? Until further missions return to sample the plumes more thoroughly or descend into the ocean itself, the true nature of what churns beneath Enceladus's surface remains uncertain. Titan, Saturn's largest moon, presents a very different but equally intriguing puzzle. It is a world both hauntingly familiar and deeply alien, covered with lakes, rivers, and seas, not of water, but of liquid methane and ethane. Its thick, hazy atmosphere and dynamic weather sculpt a landscape that echoes Earth's hydrological cycle in eerie parallel. Yet the methane in Titan's atmosphere should not last long. Sunlight should break it apart over geological timescales, meaning its vast methane seas and rainfall ought to have disappeared millions of years ago. Their continued presence implies that something on Titan is continually replenishing this methane. Cryovolcanoes may be releasing fresh material from the moon's interior, or complex surface chemistry may be generating methane in ways not yet understood. Some scientists even wonder whether this methane cycle could be a biosignature, as methane on Earth is strongly linked to life. Whether Titan's methane is geological, chemical, or biological in origin remains one of the great ongoing mysteries of planetary science. Mars, too, harbors its own ancient secrets. Billions of years ago, it was a vastly different world, with flowing rivers, large lakes, and potentially even sprawling oceans. Today, it is cold, dry, and barren, with only faint wisps of vapor drifting through its thin atmosphere. Where did all the water go? Some of it may be locked in underground ice, some trapped within minerals, and much may have escaped into space after Mars lost its protective magnetic field. Yet the complete history of Mars's transformation is far from clear. The surface bears countless scars of its watery past, but the planet's present dryness raises profound questions. Did the water vanish gradually over millions of years, or did it disappear in dramatic shifts? Could liquid water still move deep underground, hidden from view? Solving this mystery may be essential to determining whether Mars once harbored life, and whether it still might. Beyond the planets, even the foundations of our scientific understanding raise deep, unresolved questions. Mathematics, the abstract language we use to describe patterns and relationships, somehow maps perfectly onto the workings of the universe. Equations invented by humans end up predicting physical phenomena with extraordinary precision. Einstein's theories foretold the existence of black holes long before one was observed. Maxwell's equations predicted radio waves decades before anyone knew they existed. It remains baffling that symbols written on paper can reveal truths about stars, atoms, and galaxies. Some scientists argue that mathematics is discovered rather than invented, an inherent part of the universe waiting to be uncovered. Others suggest it is a construct of the human mind shaped to match the patterns we perceive. But neither perspective fully explains why the same mathematical principles can describe everything from a falling object to the orbits of distant planets. Mathematics behaves like a universal key, yet the reason it fits so perfectly remains one of the deepest puzzles of existence. Similarly, the constants of nature, fundamental numbers such as the speed of light, the charge of an electron, or the strength of gravity, appear fixed and finely tuned, yet their values have no known explanation. Adjust any of them slightly and the universe could become unrecognizable. Stars might fail to form, chemistry might not function, and life as we know it could be impossible. Scientists can measure these constants with extraordinary precision, but no theory explains why they take the values they do. Some proposals suggest they are simply accidents of cosmic history, while others imagine a vast multiverse where countless universes exist, each with different constants, and we inhabit the rare one that permits life. But these ideas remain speculative. The constants of nature are like the settings of a grand cosmic instrument, precise, unwavering, and deeply mysterious, a background melody whose composer is unknown. Even the concept of randomness, something we take for granted in everyday life when flipping coins or rolling dice, remains philosophically and scientifically uncertain, raising the question of whether true randomness exists at all or whether every outcome in the universe is governed by hidden rules yet to be discovered. Randomness seems simple on the surface, something we encounter every day when a coin flips or dice roll, Yet physics transforms this familiar idea into something far stranger and far more unsettling. At the quantum level, the universe behaves like a restless theater of unpredictability, where particles such as electrons blink into different positions without warning and radioactive atoms decay at moments that appear entirely without cause. This raises a fundamental question. Is this true, intrinsic randomness woven into the foundations of reality, or merely complexity so deep that we have yet to understand the hidden gears turning beneath it? Einstein famously rejected the notion that nature could be governed by pure chance, insisting that hidden laws must silently dictate every quantum event, arguing with his iconic phrase that God does not play dice with the universe. Yet decades of rigorous experiments have revealed that quantum mechanics may indeed possess an irreducible randomness, a kind of cosmic unpredictability we cannot peel back with deeper theory. Still, some researchers suspect the universe hides more structure than we can currently detect, while others believe randomness is a fundamental ingredient of existence itself. If true randomness exists, then uncertainty is not merely a limitation of human knowledge, but an essential feature of what the universe is. Whether reality is fundamentally ordered or inherently chaotic remains an unanswered question at the heart of modern physics. Time, too, stands as one of science's most profound and perplexing mysteries. We experience time as a steady, unstoppable flow that carries us from the fixed past into an unfolding future. Yet physics cannot fully define what time actually is. Einstein permanently reshaped our understanding by revealing that time is not absolute. It stretches and warps depending on speed and gravity. A clock high on a mountain ticks faster than one at sea level, and clocks in orbit age differently than those on Earth, demonstrating that time intertwines with space into a single flexible fabric. But even with this knowledge, we still don't understand why time appears to move only one way. Why does the past feel unchangeable while the future remains open and uncertain? Many physicists tie the arrow of time to entropy, the natural tendency of disorder to increase. Yet this only deepens the puzzle. Why was the early universe so extraordinarily ordered in the first place? Some even suggest time might not be fundamental at all, but a human-perceived illusion emerging from deeper laws we have yet to grasp. Time shapes every heartbeat, every memory, every story we live, yet its true nature remains hidden. Matter itself exists while antimatter nearly vanished, and we still lack a complete explanation for this cosmic imbalance. According to the physics of the Big Bang, the universe should have produced equal amounts of matter and antimatter, and since they annihilate on contact, everything should have disappeared instantly in a burst of pure energy, leaving behind no stars, planets, or people. Yet matter somehow triumphed. Tiny asymmetries in the behavior of matter versus antimatter have been observed in experiments, offering clues, but these differences seem far too small to explain why anything remains at all. Somewhere in the earliest moments of the cosmos lies the reason why something exists instead of nothing, a profound riddle that continues to challenge our deepest theories. Even mass itself, something that feels so obvious and tangible, carries mysteries within it. The discovery of the Higgs boson in 2012 confirmed the existence of an invisible field that permeates all of space, granting particles mass much like a swimmer pushing through water. Without this field, matter could not form the structures we see. Yet the Higgs mechanism only answers part of the question. Why does the Higgs field exist at all? Why does it have the strength it does? Why do different particles interact with it in such strikingly different ways? The discovery opened a door, but behind it lies a deeper, unanswered story about the origins of matter. Reality itself may be smooth or grainy, continuous or pixelated, and this too remains uncertain. Although space appears infinitely divisible to our senses, some theories propose that at the smallest possible scale, the Planck scale far beyond our current experimental reach, the universe may consist of tiny, indivisible units like pixels on a screen. If true, then space and time are not endlessly smooth but built from discrete building blocks, requiring a complete rewrite of many physical laws. No experiment has yet confirmed this idea, leaving the texture of reality unresolved. Similarly, while physics continually probes smaller and smaller scales, from atoms to protons to quarks, there may be a physical limit beyond which smaller has no meaning. The Planck length, unimaginably tiny, could represent the smallest unit of space, a threshold beyond which the notion of distance dissolves into a quantum haze. If such a limit exists, then the universe is not infinitely divisible and reality has a base layer, a final foundation beneath everything. Whether this smallest scale is real remains an open question. Even the laws of physics themselves present a tremendous mystery. The universe follows precise, elegant rules governing gravity, electromagnetism, quantum behavior, and more. Yet no one knows why these specific laws, and not entirely different ones, govern our cosmos. Why do these rules allow stars to form rather than letting matter collapse immediately or drift apart uselessly? Some envision a vast multiverse where countless universes exist with different laws, and ours is simply the one where conditions happen to allow life. Others believe that deeper, undiscovered principles fix the laws in place. But the origin of the laws themselves remains hidden. We can describe them but not yet explain their ultimate source. And perhaps the greatest mystery of all is whether we will ever truly understand any of this. Science has carried us astonishingly far, allowing us to map galaxies, split atoms, sequence DNA, and set foot on the moon. Yet every answer generates new questions, and each discovery opens wider territories of the unknown. Maybe one day we will understand consciousness, decode the origins of life, unravel the birth of the universe, or grasp the essence of time. Or perhaps some mysteries will always remain just beyond our reach, not because we lack intelligence, but because certain truths may be woven into the very fabric of existence in ways our minds cannot fully penetrate. The greatest mystery may not be the universe itself, but our capacity to wonder, to reach, to question, and to imagine. As you drift towards sleep, let that idea rest gently in your thoughts, the recognition that curiosity is itself part of the mystery, that seeking answers is as natural as breathing. You have just journeyed through 100 of science's most profound mysteries, spanning everything from the hidden workings of cells to the vast architecture of the cosmos. Each one reminds us that, despite everything we have learned, the universe remains richer, deeper, and more astonishing than we can ever fully comprehend. Consider all we have touched tonight: the spark of consciousness, the riddles of memory and aging, the secrets buried beneath frozen moons, the strange behavior of stars and storms, and the delicate, perplexing structure of reality. Some of these mysteries may be solved in your lifetime, others may persist for generations, and still others may remain forever elusive. Yet that uncertainty is part of what makes the universe so beautiful. To live in a cosmos filled with unanswered questions is to live in a place bursting with possibility. Each unsolved riddle is an open doorway. Each unknown is an invitation to explore. The fact that we do not yet know everything is what keeps science alive, what keeps curiosity burning, and what draws us ever forward into tomorrow. And as you rest now, letting these mysteries drift softly through your mind, notice how their very vastness becomes calming. They do not demand answers from you tonight. They simply invite you to float among them, like stars scattered across a quiet sky. Let your breath deepen, your body grow still, your thoughts soften. Imagine yourself drifting gently through the questions we've explored, moving among them as though gliding through constellations, with mysteries above and mysteries below, a galaxy of wonder expanding all around you, and you at the peaceful center of it all, resting in the understanding that the unknown is not something to fear but something to embrace. If you happen to still be awake, you may continue on to another journey whenever you choose. But for now, there is nothing left to solve, no puzzles to untangle. Only the quiet comfort of knowing that mystery itself can be a lullaby, carrying you gently towards sleep. Good night, and may your dreams be filled with wonder.